Hi, welcome to a new lecture on learning foundations for machine learning. And we'll be today implementing k-means clustering completely from scratch. So first half of the lecture will be dedicated to understanding the theory of k-means clustering and its importance in machine learning. And in the second half of the lecture, we'll be implementing it from scratch in Julia. So welcome to the lecture. So clustering is an unsupervised learning. And in a few moments, I will explain, if you have forgotten, what's the difference between unsupervised learning and supervised learning. Briefly, in supervised learning, you have labels associated with data points. In unsupervised learning, you don't know what each data point corresponds to. You just have the data and you have to learn from the data itself. And an example of this task is k-means clustering. So let's ignore what the k means in the k-means clustering is. Let's simply think of clustering. Here, let's say you are running an e-commerce company and you have a lot of customers buying different things from your platform, and you would like to segregate customers into different buckets based on their behavior. But you don't know what all different types of buckets exist. Maybe there is customer who is overspender. Maybe there is a customer who is like very frugal in spending. And maybe there are people, three different categories of people in between. But maybe depending on the product, there are only two categories: customers who are either buying the product once or who do not buy it at all. Right. So you don't know how many different clusters of customers or how many buckets of customers exist, but you would like to categorize them into different buckets by just having some data about those customers or about their buying patterns. And this is an example of clustering. And it is an unsupervised learning because before you do the clustering, you don't know how many clusters exist and which customer belongs to which cluster. So the idea is that grouping data points such that the points in the same cluster are more similar to each other. So if you say that all these points belong to customers of one particular bucket, then all those customers would behave kind of in a similar way. Maybe it is in terms of spending capacity, like the value of the products that they buy, or maybe that is in terms of the frequency of buying. Maybe they are buying low value products, but they buy very frequently. Depends on what your cluster looks like. So the goals of clustering is exactly what we discussed. Like, you would like to identify certain patterns from the data which you otherwise won't be familiar with. So if you are running an e-commerce platform, you would like to know when the customer is not buying, when something is added into the cart. Maybe you have to make some pop-up show that, hey, you have added this thing into your cart, but you have forgotten to check out. So click this link to go to the checkout page, something like that. So maybe if you can identify patterns from the data, you can take decisions to your advantage. So that is one thing. You would sometimes want to summarize data using just, I would say, 4 or 5 points. So if you have 1 million customers, and if you would simply like to say there are only 5 types of customers, and these entire 5 million customers can be grouped into one of these 5 categories, then you can cluster the data sets into different categories. And by using the centroids of this data set, you can bucket customers. And what do I mean by centroid here? It is explained in this particular data set of just two features. So here you have x-axis and y-axis. So it's a two-dimensional data set. In many other data sets, there will be many more dimensions signifying each data point. But here, what you can see is each data set has kind of like a centroid. So here, this might be the centroid. Here, this might be the centroid. Then here, this might be the centroid. Then here, this might be the centroid. This might be the centroid. And let's say this is Y, feature Y, and this is feature X. Now we can say that there are a group of customers who have the highest, in general, the highest value of feature Y, and they belong to this cluster. There is another set of customers who have the lowest value of feature Y, they belongs to this cluster. So instead of describing all the customers in this, or all the users in this particular bucket, or all the data points in this particular bucket separately, you can just describe them by the value that its centroid has. Maybe you can say that, oh, the value of the centroid in terms of feature X is somewhere in the middle, but based on feature Y, it is the lowest. Or here, this green you can say that the value of the y is not extremely high. It is one of the highest, but not the highest. But the value of x is the highest, the centroid, because the x value corresponding to this centroid is the highest among all the other clusters. So you can simplify the data or summarize the data using the centroids of these clusters. And of course, dimensionality reduction, because let's say you have 5 clusters, then simply you can, using the original features, you can use one hot encoded cluster label. So for example, if you have a data point that belongs to cluster 1, and if there are 5 clusters, then you can use a one hot encoding as one of the features like this. So 1, 2, 3, 4, 5. And one of the axis can be the one hot encoded value itself. So in fact, not one of the axis, a set of 5 axes, because the value has to be 1 along one of the axes and 0 along the rest of the 4 axes. So you can perform dimensionality reduction. Maybe you might be it might be possible for you to remove certain features and just use the cluster labels as some new features. So the reason why, as we discussed earlier, this is an example of unsupervised learning is because the label data does not exist. For example, if you were making a cat versus dog classifier, you will have bunch of images of cats, and you will have thousands of them, cats sitting, cats running, cats in different positions. You will have different backgrounds in which cat is appearing, and you will train a neural network, convolutional neural network, to learn from the patterns in the thousands of images of cat. So there will be a lot of such images of cats, and let's say a lot of images of dogs, right? So this is a dog, and you will have a lot of them. And not just that, you will have those images, plus you will also have labels associated with those images. So all the images in the cat bucket will have a label, let's say called 0, and all the images in the dog bucket will have a label, let's say 1. It can be 0, 1, it can be like a string called cat and dog, whatever, but it'll be binary, and every single image will be labeled. However, in clustering, you will have no idea in the beginning whether a point belongs to one cluster or not. You won't even know how many clusters exist. So for example, in this data set, if I told you that there are only 2 clusters, you may probably divide it by this using this line. You may say all these points belong to one cluster and all of these will belong to another cluster. But what if I told you that there are 3 clusters? Then you might say all these belong to one, this belong to another, and this belong to the third cluster. What if I told you there are 4? Then you will find another way to cluster these into 4. So the reason why this kind of clustering is called k-means clustering is because there are potentially k number of clusters possible, and the optimum value of k we have to identify, which we will discuss in today's lecture. The second thing is you won't even know in the beginning, even if you assume that the value of k is 3, you won't know in the beginning which points belong to which cluster. So it is an unsupervised learning. And only after we assume certain centroids, so here this plus is the initial assumed value of centroid. Only after we assume the value of centroid, we will be able to subdivide the points or bucket the points into different clusters. Then we recalculate these means or these centroids, and then reassign the clusters. And this process repeats until some sort of equilibrium or some sort of steady state is achieved. And we'll discuss the algorithm of k-means clustering in detail. So in short, in unsupervised learning, label data are not provided, just data is provided. The goal is to infer some kind of pattern or some kind of inherent structure that exists within the data. So we already discussed this. You may not know how many clusters are there, and you do not know which point belongs to which cluster. This is what happens in k-means clustering. Now let's look at the algorithm. Okay, how would you implement k-means algorithm, k-means clustering algorithm, if you are just given the data? The data may consist of 2 features, in which case it will be a 2-dimensional plane. If the data has only 1 feature, it will be along a single line, and it can have n number of features, in which case it will be difficult to represent using a graph. So all practical purposes, today we'll be using 2-dimensional data set because that's much more easy to represent. And the first step is initializing the clusters. So you will say that you will start with the assumption that, let's say k equal to 2 is the number of clusters that you have in your data set. Then you will select k points random k points from the data set as your cluster centroids. Let me just maybe remove the fill. Yeah. So if you have k points, meaning if you have k centroids, you will randomly select k points. So let's say you are doing clustering into two categories, then you will randomly select 2 points from the data sets as the initial centroids, and centroids are denoted by mu. Mu is also like an average, because to calculate the centroid of a given cluster, if you have a cluster of n number of data points, you take an average of that along the xy coordinates. So all x coordinates are average and all y coordinates are average to get the centroid x coordinate and centroid y coordinate. The second step is assigning data points to each centroid. So basically, if you have centroid 1 and centroid 2, every data point in the graph, you can assign to either it is belonging to the centroid 1 or it belongs to the centroid 2 based on the distance. So let's just go back to maybe this example. So here, if we say that these three are the centroid, these three pluses are the centroids. Let me reduce the size. This and this are the centroids. Then you can say that this orange point, it actually belongs to this centroid because it is closest to this guy. It is farthest to this centroid and this centroid, right? So like that, by looking at which centroid is the given data point closest to, you can assign the corresponding cluster. So that is the second step, assigning. So first is initializing the random clusters at the starting of the algorithm implementation, and second is assignment. Third is recalculating each centroid, because once you assign every data point to the nearest centroid, you have to recalculate the centroid, because now you have a new set of data points belonging to each cluster. In the beginning, you had all data points, but none of them, you did not know which cluster each of them belong to. Then you start with 3 random centroids. Then you will be able to assign, okay, which points are closest to this, which points are closest to this, and which are closest to this. And based on that, you can define a new cluster. Now, once you have a new cluster, what can you do? You can calculate the new centroid, because now, obviously, the centroid for, let's say, this set of data will not be in this edge of this cluster. It will somewhere be in the middle of the cluster. Because if you are saying that all these orange point belongs to one cluster, you can't have the centroid. Oh, sorry, I just deleted the image. How do I just want to delete the, sorry about that. Yeah, that's gone. So if you are saying that all these orange point belongs to one single cluster, you won't have the centroid at the edge of the cluster. It will be somewhere in the middle. So you have to recalculate the centroid by calculating the mean of the coordinates of all of these points. So you will recalculate the centroid, and centroid will shift slightly closer to the center. Not exactly at the center, but closer to the geometric center. So that is what we are doing in the step 3, which is updating. And now, how do we know if this centroid is good enough or not? We will know that by repeating these steps. So we repeat the steps 2 and 3. So after recalculate, we again assign centroids to every single data point, because now that the centroid has moved, some data points that were at the boundary in the previous centroid position will now become maybe another color, or it will become part of another cluster. So it can very well happen. For example, now that the centroid has moved a bit to the center of all these orange points, maybe now this orange point on the boundary might become closer to this centroid rather than this centroid. It can happen. Or if you had a point somewhere here at this boundary which belonged to this orange cluster, maybe now that the centroid has moved towards the center, which means further away from this point might now be closer to this centroid. So now you have to reassign the color or reassign the cluster of that particular data point. And you have to do this for every single data point. And in that process, some of the data points might change. It's the cluster in which it belongs to. And you have to repeat this step 2 and 3, because now after you reassign, you have to again recalculate the centroid, because if the data points which define a cluster changes, its centroid also changes. Now you recalculate the centroid. Then after you recalculate the centroid, the the belongingness, or where the data point belongs, that will again change. So you have to repeat the steps 2 and 3, which is assignment of centroid, updation of assignment of data points to whichever cluster it is closest to, and updation of centroid based on the newly assigned data points. These two steps you have to keep on repeating until there is no significant change happening, or until a maximum number of iterations is reached. You can say that you are comfortable with 1,000 iterations, or you can stop whenever the centroids are not moving significantly. Now, what are we optimizing here? In fact, what we are optimizing is something called as WCSS, within cluster sum of squares. What is within cluster sum of square? It means the sum of square is nothing but the distance between the point within a cluster and the centroid. So X is a point within a particular cluster, and mu I is the centroid of that particular cluster. Now you are taking the modulus of distance between those 2 points, and you are taking the square of that. So it's like the distance square, and then you sum that in that particular cluster. So this is all in one single cluster, and like this you do sum for all the clusters that are existing. So if you have 3 clusters, you have to do this summation for all the 3 clusters. Now J, which is the sum of square distances, which is also called as within cluster sum of square. So you will often see this WCSS term used in this k-means clustering problems. So don't worry, it's simply like a sum of squared distances from the centroid within a cluster. You are trying to minimize that, because if this is minimized, then you can say that the centroid is on an average, every centroid is closest to its respective points. If the centroids are very far away from the points, this J value, meaning sum of squared distances, will be very high. So your objective is to minimize this value. Now we will see how to implement all of this. But before all of that, in the starting, I just want to address one question which we began with: how to even identify the number of clusters. We discussed we don't know how many number of clusters exist. So how do you know if the number of clusters is 1, 2, 7, 15? You have no idea. So there is a method for doing this, which is called as the elbow method. The elbow method is nothing but you plot on y-axis the within cluster sum of squares, and on x-axis you plot the number of clusters. Now, within cluster sum of squares, obviously it depends on the number of iterations, because as you increase the number of iterations, maybe the within cluster sum of squares for a given value of k. So let's say you say that the number of clusters that you have is 2, and then you calculate the within cluster sum of square. That value itself can change based on the number of iterations, because in every iteration the centroid of the cluster might get modified a little bit. But let's say you say that you are running it for 100 iteration for every given value of k. You can calculate the J or WCSS for 100 iterations for every single value of k. And this will result in a certain value of WCSS, such that the higher the value of k in general, the lower the value of WCSS. So if you have only one cluster, within cluster sum of squares will be highest. And why is that making sense? Because let's go back to this image. If you go back to this image, now imagine that you are saying instead of having 3 clusters in this problem, you have only 2 clusters. So I just want a copy of this graph here. Okay, so here, instead of saying there are 3 clusters, let's say instead of 2, let's say you have only 1 cluster. Then after updating and after running the cluster updation or centroid updation for many number of loops, your centroid might end up somewhere over here. Now, the sum of squares is nothing but sum of this distance square plus sum of this distance square plus sum of this distance square plus like that for all the data points. Now look at the distance here. So the distance for all the boundary points from the centroid is now very high, which means sum of squares is very, very high. Now imagine the number of clusters that you have, meaning k equal to, instead of 1, it being the number of points themselves. So let's say, I don't know how many points are there here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 24. I think I counted right, but there are 24 points. Now let's say you are saying that the number of clusters here is 24. Now, when can the number of clusters be, when can the value of WCSS be minimum? When the centroid of every cluster is on every single point. So the centroid of first cluster will be here. centroid of second cluster will be here, third cluster will be here, fourth cluster will be here, like that. So, and you will have 24 such centroids, because you are now saying there are 24 clusters. I know that this is wrong. I'm not saying this is right, but I just want to show you the contrast with two extreme cases of k equal to 1 and k equal to a higher value. Now, in this case, you have these many centroids, right? Now, what is the WCSS in this case? The within cluster sum of square equal to 0. Why is that? Because within cluster, and we are summing only within the cluster. So if this data point belongs to that cluster, the distance between that data point and its own centroid is 0. Then you add that with the sum of squares for this particular cluster, for example. There, the distance between data point and centroid is again 0. So you add 0 plus 0 plus 0 plus 0 plus like that 24 times. So it will be 0. So in the extreme case of number of centroids being high, you can bring down the WCSS to very, very, very close to 0. In the other extreme case where you are saying only one cluster, the value of within cluster sum of square will be highest. And for any value of k in between, let's say for 5, k equal to 5 or k equal to 4, any other values, the WCSS will be somewhere between this very low value of 0 and the highest value corresponding to k equal to 1. So now the question is, what value of k is the most appropriate? And we can see that based on something called as the elbow method. So what the elbow method says is, the elbow point is the value of the k where the decrease in within cluster sum of square become less significant. So I'll show you a very specific example so that you can understand what exactly does this mean. So look at the transition from k equal to 1 to k equal to 2. The value of WCSS decreases from, let's say, 320 till 120, something like that, 110 or 120. So this jump is around 200. So within cluster sum of square decreases by 200 when you go from k equal to 1 to k equal to 2. What about when you jump from k equal to 2 to k equal to 3? There is a decrease of, I would say, around 60 or something like that, right? Because this is around 40 maybe. This is maybe 45, something like that. This is 105 or something like that. So maybe this is 60. Now, when you go from k equal to 3 to k equal to 4, the jump has reduced to perhaps maybe 20 or 25. And then when you go from k equal to 4 to k equal to 5, it's very less. It's maybe 5 or something like that. So initially the jump was 200. Then the jump was only 60. Then the jump reduced to 20. Then after that, the jump reduced to just 5. And beyond that, it's a value less than 5. And here, as you increase the value of k, the reduction in the value of WCSS within cluster sum of square significantly reduces. And you can define elbow point as the point where the decrease in WCSS becomes significantly smaller. So here at this, maybe you can say the k value is 4, or maybe you can say it's 3. It's depending on what you want to say the jump in the delta WCSS is. So here it jumps from 200 to 60, and here it jumps from 60 to 20, and here it jumps from 20 to 5. Maybe you can say this is where the most rapid jump happens, because here it's a factor of 3. Here also it's a factor of 3, but here there is a factor of 4. It's up to you. Now we'll see this with an actual practical example, but let's discuss some challenges of this approach. Let's also discuss where exactly is this kind of a machine learning model used. I'm sure you have heard of k-means clustering in many different contexts. So one of the challenges is that the initial centroid that you define is one of the random points within the data sets. So this can lead to different final clusters. Different initial conditions can lead to different final clusters. Maybe that is because there might be a local minima in the value of j, because you are trying to minimize this objective function, and maybe the objective function has a local minima like this, and maybe you can get stuck here. So that is one problem, and whether you get stuck here or not might be decided based on which centroids you are starting with. Then another thing is k-means clustering. Since it is looking at the sum of square distances, it assumes that all the clusters are spherical, or all the clusters belong to like a circular region. In general, in n-dimensional, it looks like all there is equal variation along all the different feature axes, but this may not be this may not be true. Maybe some features are less pronounced than other features. So assuming that cluster distribution is kind of equal across all dimensions may not be a good one. And then another one is outliers. There can have a value that is significantly far away from all the other points. So if we go back to our example of this one. So let's say you have a data point somewhere here. So you have the X and Y axis like this, and all the points are over here, all the points are here, but just one point is over here. Now this is going to rapidly, or this is going to significantly influence the positioning of the centroids, and that will completely mess up the clustering. So ideally this outlier should be avoided in deciding which all points to be considered for clustering. So these outliers can cause an issue. So these are some limitations which of course can be by being smart enough about these issues, you can take care of. Now, where are k-means clustering applied? I can tell you one experience from my own research, which I conducted. Perhaps it was almost 8-9 years ago now. So one problem statement that I worked on as part of machine vision several years ago was classifying classifying rice grains based on its image. So there are many different rice varieties: basmati, ponni, jasmine rice. There are many different varieties of rices, and we wanted to build an algorithm which enables us to classify them into whether it's belonging to ponni category or whether it belongs to basmati or any other rice category. Now the issue here was we wanted to measure the because rice grains are not circular, they are like an ellipse. It will be longer than it is wide, but some rice varieties, if I remember, ponni was a little bit thicker, whereas the biryani rice, I think the basmati one was longer. So if you plot on x-axis the length of the rice grain and on the y-axis the breadth of the rice grain, if you assume the rice is the shape of an ellipse, then you will get some clusters. So what I had was something like this. So I had clusters of 5 different rice varieties, and this is the length and this is the breadth of the rice grain, and all the rice grain belonging to one category belong to one particular cluster. And here we had to define whether a particular data set belongs to ponni rice or basmati rice. We had to find the centroid of the cluster and decide how to classify these rice grains based on the closest distance to, or the centroid where it is closest to. So this was one application that I have actually worked on, but there are more complex applications in real problem statements that people are experiencing right now. For example, market segmentation that I talked about. For Amazon or for any e-commerce platform, you have to segment the customers. You might have seen on LinkedIn, there were posts which people were posting that if you try to book an Uber using iPhone versus Android phone, sometimes people who are booking using iPhone get for the exact same location for the exact same time. So if you want to go from A to B, you are using an iPhone in one case and you are using a Android phone on another case. They have already probably identified that the person using iPhone has higher capacity to pay, and they are willing to pay more. So the price that it will be showed on their Uber app will be higher. This also applies to 2 different Android phone users, one person who has higher willingness to pay and another person with lower willingness to pay. The higher willingness to pay person apparently on Uber gets a higher charge. I don't know the truth of this, but I have seen posts where people have posted screenshots on 2 different phones at the exact same time to go from A to B. So I'm pretty sure some sort of segmentation of the customer into higher or lower willingness to pay category exists. And if you want to compress an image consists of n number of pixels. And often you will have, let's say 256 colors, for example, because you have that many different pixel value. I don't know if that means it's 256 colors because there are RGB, 3 different colors. Anyways, you have that many values for every single pixel for red, green, as well as blue. Now, if you want to compress an image by defining an image using lesser number of colors, maybe you have to group colors of similar look. So in that also you can use clustering. If you want to classify documents group documents into individual sets. So all these documents belong to articles related to AI. All these documents belong to articles related to just pure machine learning. Maybe you have to do that. So even when Vishwara, we have run a newsletter. In that, we have to perform some sort of segmentation of all the different blog articles that we write into ML, DL, AI, or sometimes LLM or Gen AI category. So there we do it manually, but we wish there was some sort of segmentation algorithm which we can implement, which automatically clusters the documents or the blog articles based on the content. So there are real actual use cases for this kind of a segmentation. Now, let's come to the second part of the lecture, which is implementing k-means clustering in Julia. The implementation is fairly straightforward. So I highly recommend you to code with me so that you can appreciate this whole algorithm. So I have already written the code snippets. The reason why I did this is because almost always some error or the other occurs when you're trying to implement things in code. So I did not want the video to become unnecessarily long. So I have already tested my code and it's working really well. But I have divided into certain meaningful blocks so that I can first walk you through different blocks of code and then we can implement it together. So first is obviously importing different packages that we will have to use. So we'll be using random for generating or shuffling arrays into random. We'll be using plots for plotting the different cluster images, basically performing scatterplot. We'll be using statistics for calculating mean. So these are the three packages that we'll be using. I don't think we are using any other packages. If we do, we can import it during the implementation. Second is we are writing a few different functions. So the first function here is function for randomly selecting k points as the initial centroid. So if k, let's say two number of centroids you want to select because you are clustering into two clusters. Here, what we are doing is you have an initial input vector which consists of all the initial data points. So let's say XY pairs is here. So size of x comma 1 means you are counting the total number of data points. Then you are randomly shuffling it, random permutation. And from that, you are taking the, which means, let's say you have 7 data points. This random permutation of size of x comma 1 means you will have a random set of numbers from 1 to 7 ordered in a random way. Then from that, you are selecting the first k numbers. So if you have 2, you are selecting the first 2 numbers from that. So that those 2 numbers means now, let's say those 2 numbers are 4 and 3. So size of x comma 1 means random permutation of size of x comma 1 means, let's say you will have something like, let me type here, 3, 4, 1, 2, 7, 6, 5, something like this. And then you will, if k number of clusters is 2, then these two, the first 2 will form the index corresponding to the first initial random centroids. So which means whichever data point corresponds to index 3 and whichever data point corresponds to index 4 in your data set, they will form the initial centroids, right? Now, this is the function for assigning each data point to its nearest centroid. So what we are doing here is after we calculate the centroid, when we call the function, we are passing, after we calculate or after we assign the initial centroid, right? Initial random centroid. We pass into this function 2 data points. One is the original data set itself, and second is the initial centroids. Then we calculate the distances of all the points from each centroid. And then we look at the indices where the distance is minimum. So for example, let's say you have a few data points. Maybe I can write here. First data point x comma y pair is 1 comma 2, 3 comma 5, and 7 comma 0. Now you're saying that, and one more, maybe 4 comma 1. Now you're saying that you have 2 centroids. The first centroid is 1 comma 1 and second centroid is, because there are 2 axes, right? So that's why it's like 1 comma 1. So this is like a Cartesian coordinate. Second centroid is, let's say, 7 comma 0.5. Now you can calculate the distance of this point 1 comma 2, x value 1 and y value 2 to this, and the distance between this point and this point is 1. So but the distance between this point and this centroid is very high. So you can say that this point will belong to centroid 1. Sorry, centroid 1. So this is centroid 1 and this is centroid 2. And you can say this guy will belong to, I think this will also belong to centroid 1. This will most likely belong to centroid 2, and this will most likely belong to 3 square. Yeah, I think this also belongs to centroid 1. I'm just doing my quick math to see which of these two centroids, 1 or 2, these points are closest to. So at the end of the day, this function assign clusters basically returns the indices corresponding to every single data point in your data set. And the index will be 1 or 2 if you are having 2 clusters. If you are saying you have 3 clusters, index will be 1 or 2 or 3. Now, you're updating the centroid here. This function, what it does is you have now the uh, data points assigned to one of the clusters. So you're saying that here, now these 3 data points, this guy, and this guy belongs to cluster number 1, which means the new centroid, this will be updated to 1 plus 3 plus 4, which is 8, 8 by 3, comma, 2 plus 5, 7, 7 plus 1, 8. And again 8 by 3. So 8 by 3, comma 8 by 3, right? And this guy will be updated to simply 7, comma 0. So this updation is done based on the clusters each points are assigned to. So what happens here is, first, this cluster point is a variable where you are finding all the points belonging to cluster number 1, because here if you look at the for loop, it's running from I equal to 1 to k. So in cluster number 1, you want to find which all points are belonging to that particular cluster, and centroid will be mean of all of those cluster points. So that is what is written here. And then you repeat it until k, because k is the number of clusters, total number of clusters you have. And this is the centroid updation. And you have the original k-means algorithm. I'm not going through every single step because it's fairly straightforward. It's just syntax, but I'll just show you where the logic is being implemented. So here, I runs this iteration, this for loop runs from 1 to max number of iterations. So max number of iterations can be 100 as you define here. It can be 1000, whatever you are comfortable with. Then you run for max number of iterations. So you first start with the initial centroid. So here you are initializing the initial centroids as random points within the data set, which is why the previous centroid is assigned as nothing. Then cluster assignment, meaning initially you are not assigning any data point to any cluster. That you will do during the calculation. So first you do the cluster assignment. So here you call the function assign clusters. And where is that function? This is that function, assign clusters. So here you will get the minimum indices, meaning here you will get for every single data point, whether it belongs to cluster 1 or cluster 2, if there are 2 clusters. Then you will update the centroid, because after you assign the cluster, you have to calculate new centroids. So that is what this is doing by the update centroid function. And then you are looking for convergence, whether the previous centroid and current centroid are the same or not. And here, if the centroid is not getting updated, basically you are breaking out of the for loop, right? You won't be running the remaining number of iterations. And then at the end of this function, you are returning the new centroid, the final centroids, and the cluster assignment. Because only if you have centroids and the assigned clusters, you can plot a very good scatter plot, which looks like what you have seen over here. Where's my plot? Like this. So here you have these pluses as the centroids, and you have the green, blue, and orange colors as the different clusters. So we also want to do the same thing in the plotting. So that's why we need finally what we care about is the value of the centroids and the cluster assignment. And we'll be initializing certain data sets. So here, for example, we have 7 data points, and each data point will be belonging to one of the 2 clusters according to this code, k equal to 2. We can also try with k equal to 3. Of course, we'll also try with a random set of values of x. Instead of 7 data points like this, we can have 50,000 data points, and we can see how it looks if you have, instead of 2 clusters, if you have 20 clusters, how the cluster would look like, and how the boundaries between 2 clusters would look like. I also want to show you that, and I want to discuss with you why the boundary looks like a straight line rather than like a curve. We'll come to that, and then finally we'll plot. So this is what we are doing all together. Now what we can do is, let's start coding. So how do we start? We open the terminal. I'm on Mac. If you're on Windows, command line. And obviously, as I always mention, you should have a Jupyter notebook as well as Jupyter notebook, Julia, and Jupyter for Julia. Sorry, Julia for Jupyter. These three things installed. If you don't know how to do this, go back to my first lecture in this series and you will understand. It's just 5 minutes, very fast. And then here I'll type Jupyter notebook to run Julia. And after opening, it should open as a local host here. All right. Now let's open Jupyter Lab once we have the Jupyter. So click View, open Jupyter Lab. I can increase the zoom a little bit. All right. So now we can implement the k-means in this notebook. So first, let us take all the required packages. So we had using random, if I remember correctly, using, oh, one more thing. Maybe we can rename this as k-means implementation. It's not IPy notebook. So it's not a Python notebook. K-means implementation. And one more thing, this has to show Julia. If not, click here and then it will open. By default, it might be Python 3, but you should pick Julia. Then statistics and what else? And we had one more, which was I think random. Yeah, no, not random. Random is already imported. Random plots, yeah, for plotting. So let's run this fairly straightforward. And next is this function for initializing the initial centroids, basically selecting random data points as a centroid. When we run this, nothing is going to happen because only the definition of the function is there. We are not yet calling the function, right? So we are not calling the function with any arguments yet. This is the function for assigning the clusters. So assigning the clusters meaning it is returning one value corresponding to every single data point, either 1 or 2. In case when there are two clusters, if there are 3 clusters, for every single data point, there will be 1, 2, or 3. We can print this and show you how this looks like. And then updation, centroid updation. I'm sorry that I'm copy pasting. I would have loved to code this from scratch. I already did that before recording this lecture, but if I do that right now, instead of this lecture being say 45 minutes or 1 hour, it will become 1.5 hours, which I did not want. So, but I can share the code file with you. Then updation of centroid done. Then the k-means function itself, we can paste it here and then run this. And then plotting. After plotting, there is one more. There is getting the data, initializing the data. Okay, so we initialize the data. Fine. Now, hopefully, this should not have any issue. We can run. So we are saying k equal to 2, and we are having 7 data points. So here, this is the result of the k-means clustering implementation for these 7 data points. This stars are the centroids, and the blue dots and orange dots are the clusters. Initially, these are all black dots. You have no idea which one is blue and which one is orange. And after the 2 iterations, there has been convergence. And then here you can see the centroids and the cluster. Now let's do one more thing. What we can do is, how did we come up with this 2? How did we know that the actual number of clusters are 2? Why not 1? Why not 3? Why not 4? So you remember the elbow method. So what we can do is, I have already coded the elbow code when I was practicing. So what I'll do is, I'll copy the elbow code from here. Not elbow code, I mean the J value. So here we are starting with WCSS, and what is that? The sum of squares of all the clusters, all the data points within one single cluster. Initially, the sum of squares are initialized as 0. Then we will find all the points belonging to one cluster, and then we will calculate the sum of those So here cluster point, every single cluster point is subtracted with the corresponding centroid and it is squared. So here there is dot because you are doing it element wise, and then you are summing it across all the different clusters. So here the for loop will run from 1 to total number of clusters that are existing, right? And then you can return this. So what you can do here is, here let's calculate for X centroid and cluster assignment. Let us, we will plot, but we'll also calculate println WCSS. And what we can do is we can start with k equal to 1, right? So when we start with k equal to 1, WCSS will be highest. Oh, sorry, I have to run this part of the code. Okay, fine. So WCSS equal to 37.07, right? When k equal to 1. Now, what if k equal to 2? When k equal to 2, it's 8.5. When k equal to 3, it's 2.5. When k equal to 4, it is 2.7. So you can see that, and when k equal to 7, it should hopefully be 0. Do you understand why when k equal to 7, it is 0? Because when k equal to 7, you have 7 data points and all the centroid of the clusters are on the data points itself, because ultimately to minimize j, the centroids will move and it will stay on the data point itself, which means the sum of distances from the centroid within the cluster, within cluster sum of square will become 0. I'm just curious to know what if this is 10? Because you don't have 10 points to start with, so it will throw an error. You only have 7 points max. If it is 6, so you can clearly see that there is a jump when you go from k equal to 1 to k equal to 2. There is a jump of a factor of, it's going from 37 to 8.5. There is a huge jump. But when you go from k equal to 2 to 3, it's a jump of from 8 to 3. So you can kind of see using elbow method that k equal to 2. But instead of believing me, we can also plot this so that you can see that the value of the elbow or the elbow exists at k equal to 2. So I'm running this for, okay, I have to call this function plot x comma max of k. Max of k could be, let's say, 7. K means not defined in main. Okay, it's k means function, so I just need to change k means function. Okay. Yeah, you see, this is the elbow plot. So what we have plotted here is, I'm not explaining this function to you because this I had already written when I was just doing a practice run. But basically what here we are doing is the same value of WCSS we calculated for k equal to 1, k equal to 2, etc. We are simply plotting. We are just storing it in a variable and we are plotting it against k. And you can see that the highest jump happens when k equal to 1 to 2 has happening. And from 2 to 3 also there is decent jump. But from 3 to 4, the jump is minimizing. So you can say that there are 3 clusters. It is possible to say. You can say there are 2 clusters also. It's kind of difficult to say because even in the plot, even in the scatter plot, let me plot it here. It's very difficult to say whether these data points of blue and orange belongs to 2 clusters or 3 clusters. You might be tempted to say these 2 belong to 1 cluster, these 3 belong to another, and this belongs to another totally different cluster. So 3 is possible, 2 is also possible. Now let's do one more thing. I have written a function for generating certain random points. So I'll copy and paste it here so that there are a lot of random points. So this function generates n equal to 100 random points. Yeah, I want to import using plots. Not plot, using plots. Yeah. So these are 100 random points that I am generating as the input X. And what we can do is X equal to, we can define these random points as the input X. So what I have done here is exactly that. So here, these generated random points with n equal to, let's say, 100 to start with, and k number of clusters, let's say it's 2, and we can run the k-means and we can plot the clusters, right? So here it generates 100 random points like this, Then I'm saying k equal to 2. I don't know what exactly the k should be, but we'll see. And then I'm calculating the centroids, and I'm having the variable corresponding to the cluster assignment and plotting it, right? So here when I say k equal to 2, this is how it looks. What if it's k equal to 3? This is how it looks. Same data points. K equal to, actually not same data points because we are generating the random points again. K equal to 4, something like this. K equal to 5. Now, this is very interesting when you increase the number of random points. Let's go from 100 to 10,000. Then 10,000 means if it is random equally distributed, it will be all over the screen. So which is why it's covering all over this, covering all this entire screen. And k equal to 4. Sorry, yeah. If you are saying that you have 4 clusters, it looks like these squares. Now, I have a question which for you to think of. By the way, this looks very beautiful, right? I absolutely love this. Why does the boundary look like a straight line? Why not? Why is it not like a curved line? The reason is the all the points along this boundary can either belong to this left cluster or right cluster, right? Because these points are all farthest from these 2 points. I mean, these 2 centroids. So this point can either belong to, I mean, it's likely that it can belong to the left cluster or the right cluster. Now, all the boundary will be all those set of points who are kind of equidistant from 2 other points. Now, if you have 2 points and what all points are equidistant from those 2 points, let's say on xy plane, in my xy plane like this, if I have 2 points, 2 random points like this, anything that is like, if you can draw a line like this, and if you can draw a perpendicular line like this. Okay, first find the centroid, the center of this line. Center of this line exists somewhere here. And if you can draw a perpendicular line like this, then all the points that will exist on this line are equidistant from this and this, because here the distance is this, here the distance is this. This angle is same as this angle. For this point, the distance from this centroid and distance from this centroid are equal, because this angle is same as this angle. So the reason why the boundary looks like a straight line is exactly the same, because all these points which exist along the boundary are equidistant from these, almost equidistant from left centroid or the right centroid. That's why the boundary in k-means clustering like this will look like straight lines. Now let's increase the k, right? So we can have some fun. So k equal to 10, it will have 10 different clusters, and boundaries are pretty much almost like a straight line. Somewhere you might see like these, like it might appear as if it's not a straight line, but theoretically it should be a straight line, because it's almost always a fight between 3 different or 2 different centroids. But sometimes the fight can be there between 3 different centroids, and I'll show you an example. Imagine you have 3 centroids. This is one centroid, this is another centroid, and this is another centroid. Which point exists such that it is equidistant from all these 3? It will be somewhere here in the middle. Now, all the points over here, and all the points, oh, sorry, not like that, not like that. All the points along this line will be on the boundary between this centroid and this centroid. All the points along this line will be on the boundary between this centroid and this centroid. And all the point along this line, I mean, this line will be on the boundary between this centroid and this centroid. So the cluster in which, this is the center will look like this. So the boundary will look like this. The cluster in which I'm just using different dots. The cluster in which this is the centroid will look something like this, the boundary. And the one for where this is the centroid will look like this. So that's why when you have 3 centroids like this, the intersection point will look like, there are some phase diagrams that you might have seen in material science. If you're familiar with that, this looks like that. So that is why you can see that when you consider 3 centroids, for example, this centroid, and this centroid, it looks like that, right? So this is the beauty, and you can see the different number of clusters. So almost always, if you have large number of data points which are closely packed, it's impossible to say the number, say how many number of clusters are there. But essentially, this is how k-means clustering works. And if actual clusters do exist, k-means clustering can can definitely cache that. If actual patterns do exist, it can definitely cache that. In our particular data, there are no patterns. It's simply random numbers. So you can define whatever the k value be, it will simply plot it like this. So I think this is a good time to wind up this lecture. I want to take a moment before winding up the lecture to congratulate you for reaching all the way till this course, and especially if you have been implementing all the code. I'm sure you are getting fairly good command on Julia language, and not just that, also on basic concepts within machine learning. You're doing exactly the right thing, what you're supposed to do. And I would say if you are at this portion of the course, you are already ahead of 99.9% of the people who will ever take this course, because the trend that I have generally seen is people start to learn something, but they rarely finish it. So I really appreciate you for the tenacity with which you are going ahead along with me in this course. And I'll see you again in the next lecture. Take care until then. Bye.